All right, welcome to day 4. Homework for tonight is packet page 30. Remember, you need that uploaded by 5 a.m. Tomorrow. Remember, also, you have problems that you can be working on that is due by 2 o'clock on Friday. That's right on Delta Math. You have 3 skills. You need to get 3 in a row on each skill. Make sure to go and do that. Those are a big chunk of points that can help your grade a lot. All right, so on your warm-up sheet, if you could pause the video and answer this question in your warm-up sheet. Once you're done writing it down, you can unpause the video and then keep going. All right, so bias, we want to be looking for groups that are either overrepresented or underrepresented by the way the data was collected. So we want groups that are over or underrepresented based on the method of data collection. So let's flip and look at the homework. So the first group, we had to tell the type of sample, and hopefully you used your notes to help you do this, because you had each of them. So anytime there's a pattern, so every 8th chip after the 3rd, we're doing a pattern there. That's a systematic sample. Stratified is when you first split into groups and then randomly pick from the groups. We did that yesterday and the day before with the rolling down the river activity. So we first, in 2 of the samples, we split uh, the land plots into either columns or rows, and then we randomly picked from those columns or rows. An example in school is maybe you would split into grades first, and then randomly select 10 people from each grade. So you've stratified by grade before you do a random sample. Simple random sample for 3 because everyone had an equal chance of being selected, and you were just randomly selecting those people. Voluntary response, that's when people have to put effort to respond. Usually that creates a lot of bias because you only get the people that are either really for it or really against it. And convenient sample is whatever is easiest for the researcher or the data collector. So it will make their life the easiest. So that's why it's called a convenient sample. In the multiple choice one, we want the most accurate results, basically saying we want to reduce bias. So cars in our school parking lot, you would probably have an overrepresentation of students. So therefore, the types of cars that students would either want or tend to drive would be overrepresented. So people that live in our states would not give a good representation of our town. Cars advertised in the local newspaper aren't necessarily the cars that are being driven in her town. And then the grocery store, well, you figure everyone's got to go to the grocery store at some point. So there should be an equal representation of different types of people going to the grocery store. So that's why that would be the best answer. Usually with those, there's a lot of ones that you could eliminate, and it just kind of narrows down to one remaining choice. So students in the library were asked their favorite type of book, and we want to know whether or not it is biased. Well, if you're in the library, you may tend to like a certain type of book as opposed to the other. So because this was only in one location, that could create bias. All right, so our new stuff for today is going to be on packet page 22. We're going to learn about two things. We're going to learn about how to design an experiment, and we're also going to look at some basic probability. So an experiment is when we do something to some type of subject, either people, animals, or an object, and we want to see what is the response when we do that thing to it. The whole idea of an experiment is we want to try and see if we can predict that response over time when we do that something to it. We want to see if there's some type of causation between the thing we do and the outcome in our subjects. Moving to the bottom of 22, the individuals in our experiment are called the experimental units. If they're humans, we tend to call them subjects. If they are objects, we would just call them the experimental units. The thing you do to the people in the experiment or the things in the experiment is called the treatment. You're probably familiar with the control from science. That's a group that you don't do anything to. You do not provide them the treatment so that you can use it as a comparison to the experimental group. A response variable is what you want to predict. So you're hoping your experiment will allow you to know, okay, if I give a group this thing, I know the response variable is going to end up like this. And the factor explains any changes that would occur in the response variable. So we won't rely too heavily on the terminology in this course, but I just wanted to introduce it to you. What we will rely more heavily on is how to design an experiment. The first step is that you must randomly assign to groups. You can't say, all right, split yourself into two groups. You need to imagine you put if in this rats example, imagine you wrote the numbers of each of the 30 rats on index cards, shuffled them up and dealt them into two piles. And that told you which rats went into each group. And then maybe you flipped a coin about which of those groups got the new diet and which got the standard diet. And then you can compare the weight gain at the end. So there's always 3 steps to deciding the experiment: randomly assigning the groups, then giving one the treatment and the other not. So in other words, the control, and then comparing things at the end. So if we go down at the bottom, we're going to see if we can actually list out the steps. We got a new drug, and we want to describe how you can have a controlled experiment. Okay, and this question was on the Regents as a part 2 question once. So the first thing we always want to do is split into 2 random groups. So that can be done again by like putting the subject's names on cards, shuffling them and dealing them into whatever number of piles you need. You could use a random number generator, but it needs to be random when you assign them to the groups, and you need to have that word random when you describe that step. Step 2, we would give one group the drug, and we would give the other group the placebo. So if you're not familiar with a placebo is just something that, like say if it's a person, they'll give you a sugar pill just so you think that you're getting the drug, because they've determined in studies that mentally, if you think you're getting the drug, you might just have a more positive attitude of the response of it, of what it is. So they want everyone to have that experience of taking the medication, so that mentally there's no difference between whether the people know they ingested something or not. And then 3 will always be the same. We'll just compare the results. Now in step 2, you could have also just said, and don't give the other group a drug. That would be fine as well. Just that term placebo is something you sometimes see in when you're working with a drug. All right, so let's try it once more just to make sure we've got it down. In this case, we're going to work with chicks. So the agricultural department, they got a new variety of corn. They've switched the amino acid content in it so that it has better nutritional value, higher nutritional value. And they want to know if the new type of corn will help the chicks gain weight. And we got to describe the experiment. So step one should always be split into two random groups. Step two, give one group the new corn. And we'll give the other the old corn. Basically the corn that did not have the higher nutritional value, or have the altered amino acid, I should say. And then step three is always going to be the same. Compare, in this case, compare the weight gain. And that's it. So if you want to design an experiment, we want to make sure we account for those three things. Always split into two random groups. Give one whatever you are trying to find out about, give them that treatment. The other do not give them, and then compare the outcome in the end. So that's it for the designing experiments. The second half of this video, we're going to talk about probability. So probability is what you want to occur divided by the total number of outcomes. The theoretical probability of something is what should happen over a large number of outcomes. If you do something a small number of times, it might not match what the actual probability is. So it describes what happens over the long run. So for example, if I flip a coin 10 times, the theoretical probability says that you should get 5 tails. But if you actually try that, you might not get 5 tails. So on the next page, this is on top of page 25, this is a little chart of two sequences of flipping a coin a whole bunch of times. So the bottom axis tells you how many times the coin was flipped and what proportion were heads. So like in the blue one on the top, at the beginning, they flipped the coin once and it must have got a head because 1 divided by 1 is 1. And then maybe here all 5 were heads. 5 divided by 5 were heads. But then notice over time in both trials, the ratio gets really, really close to 0.5. So if you do it thousands, a million times, your ratio, it might not be exactly 0.5, but it's going to be super, 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 super close because the probability is what should happen in the long run. When working with probability, we also often talk about the sample space. So the sample space is all the outcomes of the experiment. So some examples of that, if you flip 2 coins back to back, you have four possible things in the sample space. You could do a head and then another head. A head followed by a tail followed by a head, or a tail followed by a tail. So that sample space isn't too bad. But as you get a large amount of things, the sample space can get large rather quickly. So let's say you rolled 2 die, or 2 dice. Die would be singular. If you rolled 2 dice, and we're going to say they're standard die with 1 through 6 on each side. Well, we want to know what's the sample space. Well, say the first die could have a 1 and the second die could have a 1. The first die could have a 1, the second die could have a 2. The first die could have a 1, the second die could have a 3. And we could keep going like that for all the combos with the first die having a 1. Well, now let's imagine the first die had a 2. Well, then the second die could have a 1, or it could have a 2, or it could have a 3, 4, 5, or 6. So we got a ways to go because we got to have the first die be everything up to 6. So we have all the options with the first die having a 3. Then we could do all the options with the first die having a 4. All the options with the first die having a 5. and all the options with the first die having a 6. Now, often when we are working with 2 dice, I will give you this sample space listed out so that you wouldn't have to list this entire sample space, because that's a huge pain. Now, just one thing I want to point out about the way this sample space is listed that can make things easier. If you look at a slant going from bottom left upwards, so for example, let's look at this slanted part here. I want you to find the sum of each of those dice that are in those pairs. So 1, 4, 2, 3, 3, 2, 4, 1. Hopefully you notice their sum is all 5. So when you look at the diagonals going in that direction like that, they will always add up to the same thing. So for example, if we looked at this diagonal here, notice all those add to 9. Recognizing that can make counting different pairs easier. Like if you had to find which pairs added to even things, you could look at certain diagonals to figure that out. So that's just one little hint that can make counting things a little easier. So probabilities can always range from 0 to 1. If the event is definitely not going to happen, the probability would be 0. If it was going to happen for certain, it would be a 1. Okay, and then it could be anywhere in between. If you added up every outcome in a sample space, it should always add to 1. So for example, the probability of a head is 0.5, the probability of a tail is 0.5. Those are the only outcomes. If you added them, they would end up giving you 1. If you rolled a die, it's a 1/6 probability for the 1, a 1/6 for the 2, 1/6 for the 3, 1/6 for the 4, 1/6 for the 5, and 1/6 for the 6. If you added those all up, we would get 6/6, which is the same as 1. So if you added all the possible outcomes and their probabilities, it should give you 1. Now the notation you see on this page is that capital P. If you had P and then tail, that would be saying what's the probability of flipping and getting a tail. So we would say 1/2. Or if I said P and I said roll a 5, well that probability would be 1/6. Because when you roll a die, there's only one way to get a 5 out of the 6 possible outcomes. So that capital P is just a notation that means probability. The complement is basically the leftover stuff. So the complement of any event is the event that A does not occur. And this is missing. There's a notation that's missing here. These should both have a little C there. So if you could add that into, or on your packet page, this is on the bottom of page 26. So your complement is always 1 minus whatever your probability of the original thing is. So this is easiest to understand by just looking at an example. Let's say the probability of rain, let's say it was 0.2. So something I want to point out is probabilities could be written as decimals, percents, or fractions. So as a fraction, 0.2 would be 1/5, and as a percent, 0.2 would be 20%. So all those would be correct for your probability. Now, if that decimal or percent isn't going to terminate, you should probably be writing it as a fraction because we want it exact, unless it told us to round somewhere. So our complement would be the probability of no rain. So that would just be the opposite of each of these, or in other words, what would pair with it to get to 1? So the opposite of 0.8 would be 0.2, or opposite of 0.2 would be 0.8 to get to 1. Or 1/5 would be 4/5, because 1/5 plus 4/5 is 5/5, which is 1. We want to get to 100% if you're thinking in percent, so 80% would be the complement there. So basically, it's all the leftover outcomes, whatever their probability would be. So if we go over to 27, we'll list some complements. So if set A is Monday, Thursday, Saturday, we're looking at days of the week. So our complement of set A with the C, well, the things we don't have Sunday, we don't have Monday. Oops, hold on, we do have Monday. Sorry about that. We don't have Tuesday. We don't have Wednesday. We do have Thursday. And we don't have Friday. And those squiggly brackets are often called set notation. Okay, it's showing a set as opposed to, like, say, a coordinate or an interval. So our complement of B, so we do B with the little c, the opposite of at least 2 people selected out of 5. Well, if you're at least 2 people, that means you could be 2, 3, 4, or 5. So we could say less than 2 selected out of 5. Because for the opposite, we would want to make sure we don't include the 2, because at least 2 people would include the 2. You also could just, in this case, physically write out 0, 1 for your people. So the complement of no one being selected out of a group of 4, well, no, the only option for no one would be 0. So the complement of that we can word in a couple different ways. We could say at least 1 person selected. Out of a group of 4. Or you could say something like 1, 2, 3, or 4 people selected out of a group of 4. That would mean the same thing. So there's more than one way that you could notate it, but we need to somehow give an explanation of how it could be the opposite of being no one. Down at the bottom, we've got some probabilities when drawing an M&M from a bag. And we want to know what the probability of a blue is. Well, how we would go about this is we know that the probabilities have to add to 1. So the 0.3 and 0.2 gives us 0.5. 2 more gives us 0.7, 0.8, and 0.9. So adding up all those gives us 0.9. So therefore, to find the probability of a blue, it's just whatever's the leftover to get us to 1, because we know in total, when you add them up, they have to equal 1. So that would just be 0.1. What is the probability that a random M&M is any of red, yellow, or orange? Well, when you have an OR, you just add up the individual probabilities. So red's probability is 0.2, plus yellow's probability is 0.2, plus orange's probability is 0.1. So 0.2, 0.2, and 0.1 will give us 0.5. So there's a 0.5 chance. You could say that's 1/2, or you could say that's 50%. Any of those would be correct. Now, our last couple things for today, I would have polled the class if we had been live. So we'll just kind of talk through what it would look like here. So imagine I asked people to raise their hand who had brown hair. And then I had people raise their hand who had blue eyes. The people who had brown hair, we'd call them the people in set A, and brown eyes in set B. The people that raised their hand for both would be the people that would belong to set A and set B. Well, if you belong to 2 different sets at the same time, we say that they would be in the intersection of those. Now this kind of got shifted, but our notation for intersection is like an upside down U. And the way I finally remembered that in high school, because I always would mix it up, is the intersection sign is when we want them to be an A and B. And I recognize some people draw their capital A's like that. So it kind of looks like some people's capital A's, but without the bar going across. And that's how I help remember intersection. Now we're going to see this on the next page, but if you have a Venn diagram, the intersection is represented by the middle part. If this was set A and set B, the intersection is that overlap, the people who are part of both sets at the same time. Down on the bottom, if we wanted to look at people who belong to set A or set B, that is called the union. So if you are in at least one of them, you could be in both, but you got to be in at least one, we call that the union. The notation for the union is an upside down U, or you might just see or used as well. Now, union, it looks like a U, so it's a little easier to remember. Again, we'll see this on the next page, but in terms of a Venn diagram, if this is set A and this is set B, the union is anywhere we're in either of the sets. So it would be all of these three sections. The people that are in both A and B, who are in only A, and who are in only B. So on the other side, again, I would have asked people who like to text, people who like to draw. Let's say we ended up getting 3 here, 4 there, 5 there, and 2 out here. Well, if I asked you how many people like to text and draw, we would say there's 3, because there's only 3 in the middle. If I asked you how many people like to draw, we would want to look at the entire draw circle. If you look at the entire draw circle, we got to look at the people who like to text and draw and only draw. So together, there's 8 people that like to draw. If we needed to do it out of a probability, you would just do 8 out of whatever the total is. So in this case, it would be 8 out of 14 if we needed to do a probability. If I asked how many people like to text, then we would look at the entire circle for texting, and we'd take the 3 that like to do both and the 4 that only like to draw, and we would say there's 7 that like to text. If we wanted to do a probability, we would again put that over the 14 that was total. These 2 out here would represent people who don't like to do either of those 2 things. So to finish up this video, we'll just kind of do what we did on the other page. So where is the U, the union, in the Venn diagram? Well, the union is when you're in either set A, set B, or both of them. So those regions would represent the union. The upside down U is the intersection, and that's the part that is the overlap. Those are people that are in both sets A and B. And then the A with the C, that's the complement. So that's anything that's not in A. So the stuff not in A would be the people that were only in B, but also the people that were in neither. That would represent the complement of A. So you got to be in all the spots where A would not be represented. All right, so that's it for this video. You got your homework. Make sure you have it turned in by 5 a.m. tomorrow, and you can be working on your problem set, which is due on Friday.